I want to use this video to talk about the binomial distribution and how to make that work. And let me take you to, right away, a spreadsheet. Now, I use this spreadsheet other places we're talking about this, but this is the spreadsheet. First of all, this is a layout over here of heads or tails for flip of a coin. You know, if I flip two coins, I can either get two heads, two tails, or a head and a tail, tail, head. So these are permutations here. Over here, I make that it's just a combination of a head or tail. Combination means it doesn't matter which one comes first. Permutation means they come in a specific order that I would happen to draw it. In that case, what I have is a 0.25 for two heads, 0.25 for two tails, 0.50 for heads, tails. So that's just looking at these things here, the four options that possibly could come up. I do the same thing here for three flips of the coin, where I could have three heads, three tails, two heads and one tail, one head and two tails. Those are the only combinations that are possible. Here's the probabilities of those sorts of things. And here, if I do the same thing with four different flips of the thing. As gets, that should make, the point I want to make with doing this is that the number of trials that you have has a big determination on what the outcome's going to be and the probability of different outcomes. In part because the more trials you have, the more possibilities there are. There's a function, this thing comes up also, and I just want to, down here, let me insert the function here. Look at the function, the binomial distribution function. You get this dialog box comes up. Now, it's a little out of order what turns the way I think about it, but if, for instance, I want to do, suppose I ask you the question, what's the probability of getting up to 6 heads out of 20 trials with a flip of a coin? Now, the first thing I would tend to do here is say, out of 20 trials, so I want to put 20 in here as the number of trials, getting up to 6 heads, so I'm going to put 6 in here. The probability for a head or tail in this thing is a 0.5, so I add in there. And now we come to this funny, confusing one here, cumulative or not. If I say I want to get up to 6 heads, what I'm saying is I want, what would be an accurate answer to that is, you mean 1 head or no heads or 2 heads or 3 heads or 4 heads or 5 heads or 6 heads. So there are actually 7 combinations of things there in the process. But how many that's the cumulative one. If I said exactly, that's what I call, they don't use the same word here. They use the mass function when they talk about this in the dialog box here. But I think of it as the point probability, the probability of getting that specific point, which is 6. Since I have said that, here's a logical value, use true for the mass function, use for cumulative, use true for what they call the probability of mass function, use false. False for me is the point probability as opposed to the cumulative probability. Is the probability of that particular point on the distribution. Since I've said I want up to, that's a cumulative. So let me put in here true. And it tells me the probability of getting up to 6 heads. Boy, that seems low for me, but it's 0.05, about 0.06 if you round that up. So what do you suppose the probability of getting exactly 6 would be? Well, come back here and let's put in a false instead. Oops, I got to spell it right for them to notice. And then the probability drops to about a 0.04. It was about a 0.06 before, now it's about a 0.04. So it's a smaller probability to get the specific point than it is to get that point plus everything up to it. That's fairly reasonable ultimately. Now the other thing here is, since there are 20 trials, if you look over here, this is when I have 4 trials. These are all the different possibilities. So it makes some sense that that would be a much bigger thing. The number of possible outcomes gets much larger when the number of trials increases in this one. Let me just point out for you, for instance, suppose I said, well, again, let me go back to cumulative. I want the cumulative probability, 0.0, just 0.057 down here. If I say, well, I'm sorry, it wasn't 20 trials, it was 10 trials. Well, in that case, the probability jumps to 0.82. The probability of getting at least 6 out of 10 is pretty high. It's about 0.82. The number of trials dramatically influences this process. We'll go back to 20 here. Now, suppose what I say, oh, by the way, I've got a loaded coin. It doesn't come up heads every time, but it's loaded, so it comes up 75% of the time. Well, then what happens? You get this thing here. Now, I just know for this, e to negative 0.05 means you're going to move this thing, this decimal point, 5 places to the left, so it becomes 0.0000029. That's a pretty slow probability in that kind of situation. Changing any of these things, again, but the common case here is the probability is 0.5. There are some things that show up that are more probable or less probable than others. I will give you a problem at some point about the likelihood some students will drop out of school, and the probability that they will drop out of school is 0.20. That would come in here, the probability places. If I have a sample size, the trials is kind of the sample size that we're dealing with overall here. The number S is the number we're really looking, the number of successes, the thing that is we're looking for in the process. This is the binomial distribution formula and how that formula tends to work. While I'm doing this, because I've got this, just put that in, by the way, and says, oh, because that comes up there. This is not a Poisson distribution, but let me just sort of show you the Poisson distribution here and what that one looks like in contrast to it. The Poisson distribution, again, is one that what's the likelihood of something happening in a time frame? Suppose, what's the likelihood of getting 5 hurricanes in a time frame when the expected value is 0.3. Whoops, I don't want to do that. And everything up to that, everything up to 5. Now, 0.99, that's a fairly high probability. If the mean here was 0.03, oh, it doesn't make a lot of sense to me, but I'll give that time in. This is the one to focus on, though. You don't need to do Poissons in this class, but I just want you to know that it does exist out here. I showed you here, this is how you use the binomial distribution, and that's what I wanted you to hear today.